Today we're going to be talking about systems of linear equations, and we're going to be talking about the first of three algebraic ways we can determine the solutions, and that is going to be solutions by graphing. But first we need to talk about what exactly is a mathematical system. Mathematical systems are also called simultaneous equations, and that's because it is a series of two or more equations that we're going to solve at the exact same time. So the solution for a system of equations, or my two or more equations that I'm solving, is the single point where that is true for both of the equations. So what that looks like is here we have y is x plus 10 and y is 3x minus 4. Okay? This is a system. We want to solve both of these equations at the same time. What a solution looks like to this system is, for example, the point 717. If I was to substitute this point, this x and y value, into each one of my equations, 7 for x and 17 for y, to be a solution, it has to make both of these equations true. So if I substitute 7 for x and 17 for y, 7 plus 10 is 17, 17 equals 17. So the point is true for the first equation. I end up with a true statement. If we check with the second one, if I substitute 7 for x and 17 for y, 17 is 3 times 7 minus 4, or 21 minus 4. 21 minus 4 is 17. So I also end up with a true statement here. So this point, 717, is true for both equations. Therefore, this point, 717, is the solution to the system. It's the point that makes both of the equations true. On a graph, if I was to take those two equations, x plus 10 and 3x minus 4, and graph them, you'll see that that point 717, which is highlighted here, is on both the red line, and it's also a point that is on the blue line. But if you notice the big picture, that point 717, you'll see, is also the point where the two graphs intersect. Okay? So when we are looking at systems graphically, the solution to the system, the point that's going to be true or be on both of those lines, is the point where the two graphs intersect. Okay? So here I have a systems of equations that is graphed on this coordinate grid. I have negative 1/4 x plus 4, and I have 5 halves x minus 7. What would the solution be? I'm looking for the point that is on this line and the point that is also on this line. The only point that lies on both lines is right here, where the two lines intersect. So the solution to this system would be this point in blue, which is going to be 4, 3. So if I was to substitute 4 for x and 3 for y in each one of those equations, I would end up with a true statement. So my solution is where the two graphs intersect. So let's do it all from scratch. Instead of having the graphs already on the coordinate grid, let's go ahead and graph them ourselves and review how to graph equations. The first thing that I have to do anytime I am graphing equations is to make sure that the equations are in slope-intercept form. That is so I can graph the y-intercept and then use the slope to find additional points. This 3x minus 1 is already in slope-intercept form, so I don't have to change anything about it. However, I do need to fix this y minus x equals 3 to put it into y equals mx plus b format. So to do that, I'm going to add x to both sides to get y by itself. Then I'll end up with y equals x plus 3. Alright, now they're both in slope-intercept form, so I'm good to graph. I'm going to start with this one. I'm going to graph y equals x plus 3 in red. I'm going to start by graphing the y-intercept, which is 3. Then I'm going to use the slope, which in this case is 1, to graph all of my additional points. So all of these points in red would be points on this line. see if I can draw a line through these points in red. Okay. So there's our first line graphed. Now let's go ahead and do the same thing, except we want to do it for this equation. My y-intercept is -1, so I'd graph that point first. And then my slope here is 3, or 3 over 1. So I'm going to go up 3 over 1, up 3, 1, 2, 3, over 1, up 3, and then over 1 would be up here. Okay, I can already tell that this point here is the one that is going to be my intersection point. So the solution of my graph is this point here where my two graphs intersect. I notice that this point is 2, 5. So the point 2, 5 would be true for both of these equations. 5 minus 2 is 3, and then 6 minus 1 is 5. So this point would be true for both. So the solution is the point of intersection, which is at 2, 5. So a key concept for you to think of is that a system of linear equations may have exactly one solution. If my lines intersect, they're only going to intersect at one point. Okay? And so this solution, this point of intersection, is the point or coordinate that is true for both equations. Okay? It's the intersection point, and it's the point that is true for both equations. So let's look at another one to graph. Again, have to first make sure that they're both in slope-intercept form. This one's okay. This one, however, is not solved for y, so that's what I need to do first. Okay, I'm going to get the y by itself, so I need to move the 12x, subtract 12x from both sides. I now have -3y is -12x plus 6. Divide everything by -3. So I end up with y is positive 4x, negative divided by negative is a positive, and then minus 2. And here I have y is 4x plus 1. So I'm going to graph this first equation. I'm going to graph it in blue. The y-intercept is -2 and the slope is 4, or 4 over 1. So my y-intercept is -2. And then I'm going to go up 4, 1, 2, 3, 4 over 1, up 4 over 1. So this line would look like this. Now, if I'm going to use graph my second equation, my intercept is at 1, and my slope here is also 4 over 1. Ooh, that's definitely not up 4. 1, 2, 3, 4 over 1. There we go. I'm going to run out of room, so I'm going to go down 4 and then over 1. Okay, and then I'm going to draw my line to connect these points. And so now I need to look at what is my point of intersection. And the thing that I'm noticing here is we've already learned something special about slopes. And you should recall that when your slopes are exactly the same, the lines are parallel. And how many points of intersection do parallel lines have? They have none. So this is our second key concept. If the lines that you are in the system, if the two equations are parallel, that means they have the exact same slope, those lines are going to have no solution. There will never be a point where parallel lines cross. This little 0 with a line through it, this is a symbol for no solution. Okay? So if lines are parallel, there is no solution. I'll never be able to have a point of intersection for those two lines. So let's look at another example. Here I have 3x minus 5 and 15y minus 5x is 25. Again, this one's okay, but this one is not solved for y, so that's the first thing that I have to do. I will subtract 15x from both sides, bring down my negative 5y, then divide everything by negative 5. So I end up with y is a positive 3x minus 5. So this first equation, my intercept is negative 5, and my slope is 3 over 1. So if I go down here to negative 5 and I go up 3 over 1, up 3 over 1, up 3 over 1, okay? I'm not going to draw the line through it yet because I want you to see, you should already notice something about this second equation. My slope is 3 over 1, my y-intercept is negative 5. This is kind of interesting. My y-intercept is negative 5. I go up 3 over 1, up 3 over 1. This is lovely. This is the exact same line. Okay? The slope is the same, the y-intercept is the same. So where is my point of intersection? There is no single point of intersection. If they are the same line, every point that I put in red for this first equation is also going to be a point in blue. So how many solutions is that? That's an infinite number of solutions. So this comes to our third key concept when we're talking about systems. A system that includes identical lines, has the same slope, has the same y-intercept, has an infinite number of solutions. Every point on one of those lines is going to be a point on the second line because they're the same line. Okay? So just to recap, a system of linear equations can have 3 possible numbers of solutions. The lines can intersect at one point, so they'll have one solution. The lines can be parallel, and if that's true, there is no solution. There is no point of intersection. And then if the lines are the same line, they have the same slope, same y-intercept, it is infinite solutions. Okay? So that is all for graphing systems. We will be practicing graphing in class.